we present a lot of Gaussians, out-of-code training and rendering for seamless ultra-large-scale reconstruction. 3D Gaussian splatting is great. It's fast, it's accurate, and it scales well. Where does all the memory go? Of course, we need to store position, color, and covariances for all of the Gaussians, as well as spherically harmonics coefficients for view-dependent color. Then each of those properties needs a gradient during training and also additional Adam optimizer parameters. Finally, with the overhead from rasterization and autograd, we come to almost 2 kilobytes for just a single primitive. For a reference, just this little patch of scene here can take up to 2 gigabytes of VRAM during training. If we want to scale this up to city-sized datasets, we hit a hard memory wall. But we can just train the scene in multiple parts, right? Well, not always. Consider this simple example. We want to train the scene with 2 objects in 2 parts, split down the middle. Notice, however, that this part of the blue cone is only visible from the rightmost camera. The question is then, should we include the rightmost camera view when training the left blue chunk? If we don't, then the training of the blue chunk doesn't know about the surface and will just produce optimizer garbage. If we do, we now imprint the ghostly image of this yellow torus, which is no longer present during this training, into the wrong chunk. These kind of problems can happen thousands of times in a single large scene, causing severe artifacts. So what's the solution? We propose to use a larger, slower pool of memory, like system RAM, to store the entire 3DGS model we want to train. Then, in each training iteration, we select only the visible Gaussians from the current training view and send them over to the GPU. Then we execute a single training iteration and write the optimized Gaussians back to system RAM. There is an obvious flaw with the system, which is that the training view might see the entire scene and we run out of memory again. To solve this, we store several levels of detail of the scene out of core and then only load the particular level of detail that fits within our VRAM budget to train. So now we are training multiple levels of detail simultaneously. In this system, there are 2 major bottlenecks for performance. The first one is that we need to find the set of visible Gaussians as well as their detail level on the CPU. And the second is the PCIe bus, which means that we might need to send gigabytes of Gaussians over to the GPU for each training iteration. But before we can solve these problems, let's have a look at our level of detail model. Consider this toy example of 5 Gaussians. We can generate coarser levels of detail by recursively merging nearby Gaussians into bigger primitives, forming a binary tree. During rendering, we can run a breadth-first search on this binary tree to find the appropriate set of Gaussians for this detail level, also called the LoD cut. Different LoD cuts of the hierarchy correspond to different combinations of detail levels. Now, that's all standard so far, but we face a new challenge during training, which is that all of our Gaussians are constantly shifting and moving about. All the while, we have to keep this hierarchy both stable and also expand its level of detail. To do this, we propose 2 discrete operations, which are triggered by optimizer gradient signals. The first one, densification, adds new leaf nodes to the hierarchy in regions where more detail is required. The second, rebalancing, shifts detail away from regions where it is no longer needed. With these 2 operations, we can both expand and keep the hierarchy stable during the entire training process. Binary trees are cool and all, but I would like to introduce you to a very useful data structure called a sequential point tree. Originally, this was introduced in the context of point cloud level of detail, but it is also incredibly useful for 3DGS. Let's see how it works. To construct it, we start with the root node of our binary tree and find the exact camera distance where we would like to swap the detail level from just a single Gaussian to its 2 children. We then repeat the same procedure for its children and so on, until we have found a minimum and maximum viable camera distance for every single Gaussian in our hierarchy, which forms the sequential point tree. We can then use the sequential point tree to find LoD cuts by simply comparing the current camera to distance with each of the minimum and maximum viable distances. Notice how as the distance to the camera increases, the level of detail decreases, and also how each cut in the sequential point tree corresponds to exactly one cut in the binary tree. There is an assumption that is being made here, which is that all Gaussians have the exact same distance to the camera, which is reasonable for a single object, but not for large-scale scenes, where we need many different detail levels. To this end, we propose the hierarchical SPT data structure, a hybrid between a binary tree and a sequential point tree. To build it, we first find a set of Gaussians which cover a particular scene volume, and we use these as roots for subtrees in the hierarchy. Every single subtree is converted to a sequential point tree. Due to the nature of this level of detail binary tree, these subtrees will be spatially compact, forming patches throughout our scene. And since each patch is now represented by its own sequential point tree, each of them can have its own level of detail. In order to find the level of detail cut, we now do a two-step process. First, we run a breadth-first search on the coarse global binary tree hierarchy. And while we are doing this, we can already check for frustum culling of each node, which allows us to early exit out of entire subtrees, saving massive amounts of performance. Here you can see the frustum culling in action. In the second part, we now have a set of visible subtrees, and we cut each visible subtree using the sequential point tree to get the appropriate set of Gaussians to load into VRAM. And this is the result of our level of detail system. These hierarchical SPTs have a number of favorable properties. First of all, they are very fast because they are so parallelizable, easily beating out a breadth-first search on a normal binary tree. Second, they are robust to the changes that happen during training, which might cause the hierarchy to be degenerate. But because each Gaussian is handled completely independently, this is not an issue. Finally, they are incredibly memory efficient. At just 4 bytes per Gaussian, they are orders of magnitude smaller than the full 3D Gaussian information. And this means, very crucially, that we can store them on the GPU for our entire large-scale scene. Then we can find the level of detail cut in parallel on the GPU and request those exact sets of Gaussians from the CPU. With that, we have solved bottleneck number 1. No more slow CPU cuts. Let's have a closer look at bottleneck 2, the PCIe bus. To alleviate this, we introduce a light GPU-side cache. For example, if in one training iteration we load a particular level of detail to train onto the GPU, we don't just want to write it back immediately, but keep it around as long as it is useful. For example, in the next training iteration, the green subtree is reused again at a similar level of detail. So we don't need to do anything, but we can just keep the current level of detail in memory and train it for another iteration from a different view. The blue subtree, however, has changed significantly in its level of detail, so we need to evict it from the cache and load the new level of detail. Our full procedure now looks like this. We use the cache and SPTs stored on the GPU to find the set of Gaussians that we need for the current training view that we don't currently have resident. These are requested from CPU RAM and loaded into VRAM. On the GPU, a single training iteration is executed, and then only those Gaussians which are evicted from the cache will be written back to out of core. The result of this, we can train across street view, aerial views, and everything in between for large scales seamlessly. And finally, no more scene splitting artifacts. The key thing I want you to take away from this presentation is that splitting the scenes for large-scale training fails if the camera distribution is complex. Instead, we can bound VRAM usage with training time level of detail and out-of-core memory. Finally, if we take our procedure and drop the write back to CPU, we get an efficient out-of-core LoD renderer for massive point clouds on consumer hardware. For example, this model with 150 million Gaussians is being rendered with LoD and streamed to the GPU on a single RTX 3090 GPU. Now that is a lot of Gaussians.